Tiene todo el esquema.
Tiene que estar muy urgente. Que hoy debería ser. Si no fuera así. Con fecha de hoy.
Okay, so we are going to proceed to the presentation of the master thesis presented by Adrian Garcia, which is entitled Dynamics of Attractive Brownian Particle. Adrian?
Yeah, first of all, I would like to express my gratitude to my supervisor for the special effort done these last 2 weeks by the special circumstances. The clustering of particles is a very interesting field of research, since it could be applied to many different systems, such as colloids, in which a small particle is suspended in a liquid by thermal activity, and it can form self-assembling colloid crystals. Also, galaxies are self-gravitational systems, and the particles tend to collapse and form galaxies. And even in biology, we can observe how the organism tends to coalesce and form clusters. My work is based on this paper published by Delfau, Cristobal, and Emilio at Physical Review the last year, entitled Pattern Formation with Soft-Core Repulsive Brownian Particles. On this paper, they show how Brownian soft-core particles can form clusters with repulsive interactions, which seems counterintuitive. Here it's a plot of the paper. Here we have the spatial distribution, and here the time distribution. And we can see how the particles form clusters, even with the repulsive interaction. In the paper, they done a linear analysis of stability and show how under some conditions on the potential, these clusters are formed, which is very, very surprising, I think. My work starts with the same model as they said, but with attracting Brownian particles. I will focus on the 1D problem, and I perform almost the same analysis as they have done. First of all, I will show you some particle dynamics and present you the model, and then I will study some cluster properties, such as the diffusion coefficient, the size of the cluster in the continuous description, and the critical point for cluster formation, and the properties that have to be accomplished in order to have the cluster. These are the objectives of the work, so I will present you now. First of all, the model. This is the velocity equation that we have used. We are in the overdamped condition. Here we have the velocity of the particles. Here the potential, which is square waves. Here we have the diffusion coefficient and the Gaussian noise. We remind that we are at the attractive interactions model, so all the particles tend to be close to each other. The potential that we will use is a Gim alpha potential. It's a family of potential with this form, where epsilon is the magnitude for the potential, r is the interaction range, and alpha is like a modulation of the profile. Here we have some plots of the potential. For alpha 1 we have the red line, which is very long-tailed, but as we increase the alpha, the potential turns more box-like, so the tail decreases. We will implement this with a Milstein method and applying periodic boundary conditions. Here are some special temporal dynamics. Here we have the spatial distribution and the trajectory, the time distribution. Here are 3 different plots for 3 different values of alpha. is the only parameter that I changed to make these plots. As we can see, at a certain time, for example, 3 seconds, as alpha increases, the number of clusters increases. The number of particles is constant in all of the plots. So the main difference is that the number of clusters is different as alpha increases. Sorry, as we can see, the clusters tends to forms at a very short times. The clusters are formed and tend to collapse and form fewer clusters as time passes. We can see here that we have many clusters, but at the end of the simulation, we only 5 clusters remain. So it's obvious to think that all the clusters at extremely long times, all the clusters tend to collapse in one unique cluster. So in order to, since we are studying the steady solution, the steady system, we will focus on the study of one cluster, of one isolated cluster. Since we don't have to wait, we don't want to wait for extremely long times in order to have one cluster. We will set the initial conditions like this. All the particles will be set at the neighborhood of L half L. So we will only generate one cluster. With this cluster form, we will proceed to study some cluster properties such as its diffusion coefficient, the size of the cluster, and the critical point at which the cluster is formed or not. First of all, the cluster diffusion coefficient. Here we have the Brownian diffusion coefficient for one particle in 1D, the general case. Here we have plot one trajectory of one of the cluster with all the particles set at the neighborhood of the middle. Here it's assumed plot, and we can see that this green line is the center of mass of the cluster. So we compute the center of mass of the cluster and apply the same analysis to one particle, and we can see that the cluster behaves as one isolated Brownian particle. After some algebra and applying the equation showed before, we arrived at this relationship, and since we are at the time independent, we can say that the diffusion coefficient of the cluster is given by the diffusion coefficient of the particles divided by the number of particles inside the cluster. Here's for the case alpha 2. But this could be repeated for all the alpha that we want. In order to check that result, that this relationship is true, we compute this is an analytical result. So we want to compute the numerical diffusion coefficient, which is defined as the square displacement of the center of mass in this case. So this is what we have done here. Here we have the time evolution of the cluster, and here we have computed the square displacement of the center of mass averaged. The error bars are the standard deviation of the average trajectories, since we have to do a lot of trajectories. Here we have done 300 trajectories. And then we perform a linear fit. The theoretical value for these parameters is this one, and the numerical value, the blue line, is given by this value. Are very close, but the error is not completely inside the deviation. But we can see that the two lines are very similar. So it looks like the previous relationship accomplishes with these simulation parameters. Since the diffusion coefficient of the cluster is independent of epsilon, which is the magnitude of the potential, and r, which is the spatial range, the spatial interaction range, we can compute the same as done before, we can compute the diffusion coefficient, but with varying the epsilon parameters and the R parameters. So here we have the diffusion coefficient cluster, and here we have the epsilon. So we have done the same analysis done here, but with different values of epsilon, and here with different values of R. As we can see, the values are changing, but the change is not monotomically. So gives us the idea that it could be independent. Note that the difference between the values is very small. So looks like it's truly independent, but maybe we could improve this result by averaging more trajectories. For studying the size of the cluster, we have used the Dean-Kawasaki equation, which is presented here as the deterministic part. The Dean-Kawasaki equation is the expected density evolution in the Mill field approximation. We simplify this equation by imposing zero flux, so this disappears, at the steady solution. We define the size of the cluster as shown here. At each time, we compute the center of mass of the cluster, and then recenter all the particles to x0, for example. So if we plot here the center of mass, it will be a vertical line. After doing this, we compute the density. We divide the spatial variables, spatial space, in very small cells, and we compute all along the trajectories how many particles are inside these cells. So an histogram is generated, and we define the size as the distance between here and here, which is the half of the maximum height of the histogram. After some algebra, using the Dean-Kawasaki equation and applying the conditions imposed, we arrive at we arrive to this relationship, which is the size is proportional to the diffusion coefficient of the individual particles to the 1 divided by alpha, being alpha the modulation parameter shown before. In order to check this theoretical result, we compute the size for different trajectories, changing the diffusion coefficient. Each of these points is the log of the size versus the log of the diffusion coefficient used to compute that size. We repeat this plot and fit a function of this kind to different values of alpha, and plotted here. Here we have alpha 2, alpha 3, alpha 4 to alpha 6, and here we plot 1 over b, being b this coefficient or this coefficient. If the relationship shown before, which is here, this line should have a slope 1. The computed slope is here, so it looks very close to the value. If we add the error, it's fully compatible with that. So it looks like the theoretical value is proved. Finally, we study the critical point for the cluster formation, and we perform a linear analysis stability of the homogeneous solution by introducing a small perturbation of the form of exponential to the equation of the shown before. We obtain a growth rate of the perturbation with this form, being k the wavelength, the separation between patterns. D with tilde is the adimensional diffusion coefficient, and hat b is the Fourier transform of the potential. Here we have plotted some growth rates with different values of d. The interesting value is d equal to d critical, which has the critical value of k at k0. So if the k critical is k0, the growth rate is 0, and the critical value, the diffusion coefficient, is the Fourier transform changes of sign. If we integrate analytically the diffusion coefficient shown before, we obtain that the critical value is given by this relationship, being gamma the gamma function, alpha the modulation parameter, epsilon the magnitude of the potential, rho 0 is the initial density, since we are at the homogeneous solution, and R the spatial range of the potential. Here we have done some simulations of as before, but we have compute at the alpha 2 case the density, the maximum density and the minimum density. The maximum density is plotted here, and the minimum density is plotted here. So if we have patterns, we will have the column of the cluster at the trajectory plot and empty space. So if we have cluster, we will have the minimum density at value 0. So we will have empty cells of the space and cells with very high density of particles. If the cluster is not formed and all the particles are moving along all the spatial distribution, we will have the particles with the homogeneous solution. So 1. We will do the same analysis, changing d, the diffusion coefficient, and changing epsilon, the magnitude of the parameter, the magnitude of the potential. The vertical black line is the analytical result computed by the relationship shown before. Here we can isolate epsilon and obtain the critical epsilon, which is plotted here. The theoretical value for alpha 2 is shown here. So we can see that the cluster formation region is very close to the theoretical. Finally, to sum up, we have studied some properties of the cluster. First of all, we have studied the diffusion coefficient of the cluster, and we have seen that it depends on the diffusion coefficient and the number of particles of the cluster. Then we have studied the size, and we have seen that it depends, and it's proportional to the diffusion coefficient and the modulation of the potential, the tail of the potential. And then we have seen that there is a theoretical critical point at which the cluster are formed, and this theoretical critical point depends on all the parameters. And we have studied how this relationship is true for the critical and epsilon critical. Some further work that can be done. The next logical step will be setting this model in 2D and 3D. Also, we could study how the number of clusters evolves as the time passes. As we have seen before, the clusters tend to collapse. And it would be interesting seeing how, at which time, or which times could this happen. So, how the number of clusters evolves at different times. And last but not least, we could implement other interaction potentials, such as the gravitational potential, which is 1 divided by r. But it will need a few touches on the code, so it's not very easy to do that. Thank you for your attention, and if you have any questions.
Thank you. Okay, so now proceed to the questions. Yeah. Yeah.
interior part.